KC2JJM, Robert Griffin is a ham up in New York. He lives on Long Island, and he's a tremendous experimenter, and he's a professional software developer. And he's always in his spare time trying to make new cool applications, especially for DX work in amateur radio. His website, dxtra.com and company, actually publish these, and they're used by a number of radio manufacturers and things to integrate, and other folks to integrate into their product. So unfortunately, Bob got caught up and he couldn't make it this time, so he asked me to give his presentation. And so what Bob has done, to give you a quick overview, is to use the DX cluster servers, the spot servers, to suck all that data in and then use that to train a machine learning network to try to predict sunspot activity, taking in solar weather data, and predict where the good DX is, which is what we all want to know. So today, please sometimes we'll just let Bob's words speak for themselves. We're going to present his work on using DXtra's database for HF propagation modeling. This project combines amateur radio DX spotting data with machine learning to create predictive models for radio propagation conditions. These models can help operators determine optimal bands and times for contacts, especially for DXing and in contesting. The realization of this project has been made possible by the remarkable revolution in open source software that we've witnessed in recent years. Libraries like pandas, Redis, and piHAMtools have democratized access to powerful data processing capabilities that would have required specialized barriers to entry for complex data analytics projects in amateur radio. Even more transformative has been the emergence of AI coding assistants. These tools have fundamentally changed how we approach software development, enabling rapid prototyping, suggesting optimizations, and helping troubleshoot complex issues. Without these AI assistants, the development timeline for this project would have been significantly longer, and certain sophisticated features might have remained beyond reach. What once would have required a team of specialized developers can now be accomplished by a motivated individual with domain expertise and the right AI tools. So first of all, he gathers this DX spotting data, and I think something's zoomed out here. Well, I'll just keep going. I hope this is the too big issue. So what he does is he's able to download comma-separated value files from the DX clusters. Those of us here whose Excel guruship may have been nipped in the bud a little bit, a CSV file or comma-separated value file is the lowest common denominator of data interoperability, either between computers or applications on a given computer. So what he does is pull in all these DX spots. He's pulling in about 30,000 of them a day and putting them into a flat file or a comma-separated value file. He's collected since April 2024 about 3 million DX spots to use for machine learning training. All right, so these are some of the key data fields that he uses to pull into his spot database. Things like call sign, country and coordinates, frequency band, timestamp, and the space weather parameters for the time that that particular spot was tracked. So a little bit about space weather, of course. What we're really trying to do here is predict propagation, so we need to tie in the latest space weather. For those of you who may be living under a rock or who only operate 2 meter bands or above, we are at the peak of solar cycle 25. We're approaching peak activity. Automated spot collection data with Python to a CSV file is what he uses, and he uses several key Python libraries. First of all, he uses the telnet lib in Python, which allows you to create a raw socket connection and actually bring the data in across the internet from the various DX cluster servers. piHAMtools provides call sign lookup, band calculations, and distance and heading. And it offers comprehensive amateur radio functions for Python. It also handles Maidenhead locator calculations, DXCC lookups, and more. He's also using PyTZ, which is how he manages all these different time zones that we have that comes out of the various cluster spot data. He also uses interval tree, which is a Python set of Python libraries for dealing with intervals, and then Python itself, as you all may be aware, is a very, very, very powerful scripting language. And so it handles all parsing and CSV file implementation without having to hard code all that, just by throwing a few lines of code around. So what we use here is a TCP socket connection, or a telnet connection, as Bob likes to say. And so this is the Python code here. That's a loop in Python. And there's a little bit of snippet of code for you real true gearheads out there that he's, like Steve Gears here, he's actually using to pull this data in from the cluster. So the big thing about these socket connections, though, is we know socket connections are unreliable, as we've all tried to download things off the internet. And so the big thing here is building in robust error handling and recovery. And so it monitors, the Python telnet library monitors that connection for you in real time, has automatic reconnection after 60 seconds, logs errors, maintains a collection state. But the main thing is with the try except block in Python, we can use that throw and trap capability in the Python language to catch errors without, once again, really having to get down and write a whole lot of code to do that. So here's an example of his systemd unit file. Those of you whose Unix knowledge goes a really long way back like me, we would have put this information in the old init tab and used init. And so if you can see here, this is a unit file for the clustered telnet spider. The after network.target means that systemd will not actually try to launch this service until after the network is up and running. It's a single process is only allowed to run under the user dextra. And sets its working directory before it launches it. The big thing is this restart always, which is, once again, we would have put this type of process launched out of the init tab in the old days. Systemd does all this. Restart after 60 seconds. And the main thing is wanted by down here at the bottom, for those of you who may not be familiar with systemd unit files, that's saying that don't bring this up until the system is up fully in multi-user operation. And for those old timers like me out there, this is what we used to call run level 6. So once we get the data in here, we're going to use pandas and Redis for high performance data handling. We're going to load all of this into a pandas data frame, which is this really, really, really powerful in-memory data indexing library that's out there. And we're going to use pandas for data processing. That efficiently handles multi-million row data sets in memory. It provides powerful filtering, transformation, and statistical analysis, and handles time zone conversions. And you can load 3 million records in seconds with parallel processing. The reason we're doing this is to be able to feed these machine learning algorithms very quickly index sets of data. Now, Redis is an in-memory database, and those of you who have worked with database programs like SQL know that the long pole in the tent is going out to the disk and making these queries, and even if you have it highly indexed or whatever. But Redis works by having all its data and everything all in memory. So you've got ultra-fast lookup and retrieval with microsecond response times, and it uses set-based operations, and you can do multidimensional indexing to explore these complex data relationships to feed these machine learning algorithms the data that they need. In order to make this all work, we've got to leverage parallel processing to get the response times that are necessary. So what he did is got a server that had 88 cores, so it can run 88 parallel threads simultaneously. They're actually available on eBay these days, really cheap. So it's got 512 gigabytes of RAM, and it can handle years of spot data without performance degradation. And then to use the very latest Linux hackers out here will recognize the ZFS file system. So here's where we took the multi-threading ability of Python to process chunks in parallel, and each file chunk is assigned to a dedicated worker process so that we can simultaneously parse through this 3 million record database. Now, Redis allows us to index all this in multi-dimensional ways, so we can make these really complex queries into it, like I want to see all the spots that went between New Jersey and Japan on a Wednesday evening, that were when sunspot numbers were a certain value, and we're going to use that for the machine language training. So what we really want to do with all this, though, is create propagation analysis. So our Redis implementation employs set-based indexing for instantaneous lookups. So we can do real-time querying in the database. We can create set intersections to create propagation charts from CQ zone to a specific country in just 3 seconds. So once again, Bruce is messing up my thing here, but that's okay. We'll just keep going because we're running out of time. The main thing here is to talk now about how the AI model actually is able to do predictive analysis on this. And the question you're all asking about is, well, where's the AI in all this? But once again, this is kind of like my talk. This is how we create the training data that allows our machine language model to actually make predictions based on the real world data that we picked up from the DX cluster servers. And we're actually going to use a hybrid approach here, which, as I discussed earlier in my talk, uses several different machine learning techniques. So the bottom line is here, to make a long story short, is you can make predictive analyses to create data visualization charts like this one. This is a chart that was created by the machine learning algorithm trained by the DX cluster data, showing you when would be the best time and the best zone to go between New Jersey and CQ Zone 5. So future work. This is what Bob wants to do to expand his product and commercialize it, make it available for radio amateurs. He wants to expand data collection to include all of the data clusters, DX clusters worldwide. He wants to add receiver data from the reverse beacon network to get additional information on propagation in real time. He's developing a web-based prediction tool for operators, and we've seen some demos of that. He also integrating the FCC call sign database for more accurate distance calculations, implementing advanced machine learning techniques such as XGBoost for improved prediction accuracy, deploying a vector database to help retrieval augmented generation in the LLM query model, creating a conversational interface for natural language propagation queries. If anybody has questions about this, you can reach out to Bob, rtg@dextra.com. Come by and see us in booth 1811. I'll get you his contact information. One more thing, Bob's got a new product coming in fourth quarter 2025. I've seen this actually in action at the Ten-Tec plant. It's a real-time HF speech-to-text black box. It really does it. Steve's seen it. Works great. Those noisy HF, does noise reduction as well. It can even identify the speaker on the other end by the sound of their voice, and it'll be integrated in all the new Ten-Tec HF transceivers. Come and see us. What's the booth? 1807? 1807. All right, guys. Thanks for your time, everyone, and thanks again to Dr. Cohen and Dave Bart here for putting on this great forum.